So we have been talking about root locus, and I would like to once again start with what it is, and I would like to describe what it is. So one thing that I would like to mention about root locus is that the name root locus, when you translate directly, does not reveal much of information. So maybe it is better to say something like this. So it is actually not the locus, but also the trajectories of roots. So they are root trajectories. And they are root trajectories of what? They're actually a polynomial. They are the roots of the polynomial d of s plus k times n of s equals 0. So we change k from 0 to infinity, and we are interested in the roots of d of s plus k n of s is equal to 0 equation. Okay, so as a matter of fact, these root locus can be said that the trajectory of the roots of d of s plus k n of s on the s-plane. So I will write it over here. It is trajectories of the roots of d of s plus k n of s equals 0 on the s-plane. So in the sense that for each value of k, we are finding a root of these equations and plotting them on the s-plane. So I will show you once again on the web page, because we didn't have the chance to talk about the material on the web page. So if I go there and show you that. Okay, on our web page we have the brief description. So we have the open loop transfer function as follows. We are looking at the roots of this guy over here as k change from 0 to infinity. And we said that, okay, this has to be done by checking the magnitude and angle conditions. And by using those conditions, we derive a number of rules, which you know already. So I will jump directly to the example over here. So consider the open loop transfer function, which is equal to k times 4s squared plus s divided by 3s cubed plus s plus 1. So what we would like to do is that I want to compute the characteristic equation of this system. Okay, so suppose this is a unity feedback system and this is the open loop transfer function. I will compute the closed loop transfer function, and the closed loop transfer function has the denominator ds plus k n of s as follows over here. And I would like to plot the roots of d of s plus k n of s on the s-plane. I will also plot the step response of 1 over d of s plus k n of s and see what happens over here. So as you see over there, these are the pole locations, the roots of d of s plus k n of s. For each value of k, we are plotting them on a timeline. And for each value of k, we also see the step response of the system. And as you can see, at first the poles of the closed loop system are on the right half plane, and the system output is unstable. So you have the oscillations with increasing magnitude. And as k increase further, these oscillations get smaller, the magnitude of these oscillations gets smaller, and at a certain stage we have an underdamped response. So these are the dominant poles, all right? So dominant poles are here, and they exhibit an underdamped response for the step input. This is the pole that is neglected, its effect is neglected, and we see the regular underdamped response on our plot. And when the poles are on the imaginary axis, here it is, so when the poles are on the imaginary axis, then we have sustained oscillations in the step response. So you see oscillations here, which is neither increasing or decreasing amplitude, so they stay forever, somewhere over here. Okay, we know how to find this specific k value. We can find it by the intersection of the root locus with the j omega axis. And if you plot the root locus of the same transfer function of our original problem, you will get something like this. This is the root locus. And if I plot the roots of d of s plus k of n of s on the root locus, they will coincide. So what we are plotting as the root locus is actually are the pole locations or root locations of d of s plus k n of s, but we do it in a timeline, all right? So by the way, note that so we are doing this roughly in the sense that, for example, by applying the rules of root locus that we have considered so far, I can find this location, this is a break-in point, right? I can find this location, this is the intersection of the root locus with the j omega axis, but I don't know, for example, what happens here. This can be like this can be like this. There's a specific curve here, I don't know that. So such details are not revealed in the rough sketch of root locus, okay? So we are sketching the root locus as an approximation, but which is enough for us to make the, for example, choose the k value that makes the system stable, etc. All right. So another way to think about it is that, so for example, if you're into photography, we are for each value of k here, we are evaluating the roots of that polynomial, right? And we are plotting that in time. So that looks like also information, the k as k changes from 0 to infinity is like a collected information of all these pole locations. So that might look like a long exposure photography, for example. If you have a long exposure photography, then a photograph, then you will have a photograph where each point is extended into lines. For example, I do have here a long exposure photograph of a highway. So remember that each of these lines corresponds actually from the headlights or the tail lights of the cars over here. But if you collect those in time as you change the variable, and you will have end up with lines over there, and root locus somehow looks like this. Okay, it's a similar concept. Okay. All right, so here's our first example. We have a proportional controller and a plant over here, and we would like to plot to sketch the root locus for this system. Okay, and the open loop transfer function is given as k times s plus 1 divided by s times s minus 3. And I was just saying before, I noticed that the window wasn't visible. It is in the standard form that we are used to, k times n of s over d of s. These are the open loop zeros, and these are the open loop poles. So let's try to sketch the root locus, and I will start by plotting the axis on the s-plane. Okay. And I can open up more space here. And another one over here. Okay, so let's start by placing the open loop poles and open loop zeros. So where are the open loop zeros? So there is one at -1. So this point be -1. And I have 1, 0 over there. Where are the open poles? There at the origin and at 3. So let this be point 3. And let this be the origin over here. As you know, we do have a set of rules for plotting the root locus. So for example, the number of branches is let me try to write them down right. So number of branches is maximum of m and the degree of the numerator and degree of the polynomial. So this is equal to 2 this time. And we can also find the number of asymptotes. So number of asymptotes is equal to n minus m, right? And here we have 2 poles and 1, 0, so it is equal to 1 over here. Then I can find the angle of the first asymptote. First asymptote is equal to pi over 1, which is equal to pi. All right. So in this root locus, we're gonna have only one asymptote, and its degree has the degree pi. So it will be something like this. Sorry about this. So this is our one and only asymptote over here. Okay, and let's also plot the part of the real axis included in the root locus. So for that thing, we need to count the number of poles or zeros to the right of any test point. And as you see over here, if I pick a test point beyond this guy over here, it's not going to be included. By the way, I can write down here 3, right? But if I pick a test point between 0 and 3, that will be included in our root locus. So this part is included in the root locus, and that part is included in the root locus. Wherever it goes till infinity, and nothing else, right? So, and remember the beginning and end points of the root locus. So remember, the beginning of the root locus was the open loop poles. So we're going to start from over here, and each of these branches is going to end up either at a 0 or infinity. So there are two poles over here which will move towards each other because this part is included in our root locus. But at a certain stage, one of them should go to the 0, the other one should follow the asymptote which goes to infinity. So for that thing to happen, what are the scenarios? So one scenario is that, which is actually the only scenario, these two guys move towards each other, right? As I'm increasing k, all right. And at a certain point, they will break away, okay, and pass to the left half plane over here and meet on the real line somewhere over here. I don't know the exact locations, but it will be something like this, okay. And once they move towards each other, they will meet here at the break-in point, and one of them will move towards the infinity following the asymptote, the other one will go to the 0 over there. Does that make sense? So we said that all the root locus should start at the open loop poles and end up with the either asymptotes or the zeros. So each of these poles, one of them is going to this 0, the other one is going to follow the asymptote, and that is only possible if they only pass the imaginary axis and meet here once again. But we can verify those because, for example, we can find the intersection with the j omega axis, and we can find the breakaway and break-in points, right? So, for example, let's find the breakaway and break-in points. So let's try to find them. Break-away or in points. So you remember that we had the equation, so d prime of s n of s minus m prime of s d of s is equal to 0. So solution to this equation gives me the break-in or away points. So d of s is equal to s squared minus 3s. So d prime of s is 2s minus 3, and n of s is equal to s plus 1 minus m prime of s is equal to 1, and d of s is equal to s squared minus 3s. Okay, so what is this guy equal to? This is 2s squared minus s minus 3 minus s squared plus 3s equals 0. So let me go down, let's scroll down a little bit. So this is equal to what? S squared plus 2s minus 3 equals 0, which gives me two s values, right? So this is equal to s plus 1 times, sorry, s minus 1 times s plus 3, and I have two s values over here. So s1 is equal to 1 and s2 is equal to minus 3. So remember that this equation, solving this equation alone was not enough. We need to also check the k values. So let me write it over here. So check k values. So how are we going to check the k values? For each of these s over here, the roots over here, I need to find the k value from d of s plus k n of s equals 0. So I will check this when s is equal to 1 and s is equal to minus 3. Okay, and when s is equal to 1, so for s equals 1, we can find k as 1, and when s is equal to minus 3, or s equals minus 3, k is equal to 9. So good news is that both of these k's are positive. So because we need to check the k values, they should be positive, right? So we can find roots over there which corresponds to non-positive k values, then you're going to discard these points. But here in our case, we have two breakaway or in points, and one of them happens when k is equal to 1, the other one happens when k is equal to 9. So from this information, we can see that this point is the breakaway point. Okay, so let me write here with another color like this. So this is breakaway points. Why? Because these two poles come together and break away to complex conjugate poles. And when these two poles meet here on the real axis, they're called, this point is called the break-in point. So, break-in point. Okay. And apparently this point is equal to s, when it happens when s is equal to minus 3. So this is minus 3. So this is minus 3. And this is when s is equal to 1. This is 1 over here. Okay. And corresponding k values are, I can put it right over here maybe. So this happens when k is equal to 1. K is equal to 1. And this happens when k is equal to 9. So far so good. One of the missing things is that when do we pass this imaginary axis? So do you remember how we find the intersection with imaginary axis? So there are two ways. You either write d of s plus k n of s and replace, so let me write intersection with imaginary axis. So you either write d of s plus k n of s and replace s with j omega, or you apply Roth-Hurwitz method. So let's try to apply the Roth-Hurwitz method. So d of s was s squared minus 3s and plus k times n of s was equal to s plus 1. So that is simply equal to s squared plus k minus 3s plus k equals 0. Okay, so let's apply the Rath-Hurwitz method. By the way, you can explicitly find the roots of the second order equation, but let's enjoy the Rath-Hurwitz. So I will start from the highest order term s squared, then s and s to the power 0, and I will write down the coefficient as 1 and s to the power 0 term k. The coefficient of s term is k minus 3, and that's equal to 0. And if you do these computations, this guy is going to be, the last term is going to be k over here. All right, so first of all, for stability, all of these, the first column should be all positive, right? So the system is stable then when k is greater than 3. So system is stable if k is greater than 3, because there are no sign changes in the first column and they're all positive. But when k is 3, we have a 0 over here. So when k equals 3, we have a 0. And if we have a 0, what we do is to go one step up and construct an auxiliary polynomial p of s is equal to s squared plus k, which is equal to s squared plus 3. This is a factor of our closed transform. So root of this equation is the roots of the characteristic equation for that specific k value. And here we can find s1 and 2 as plus minus square root of 3 k over here. So we found the intersection with the j omega axis. So if we go back to our original plot, so apparently these points are so this is square root of 3j, and that point is minus square root of 3j. So that completes all details of our root locus. Let's check out another example. So in our next example, characteristic equation of a system is given as s to the power 4 plus 3s cubed plus 3s squared plus s plus k equals 0. So we would like to sketch the root locus for k changes from 0 to infinity. All right. Sorular, I see your questions over here, so let me try to see them, read them. I will start from Hussein question. So Hussein asked that, so do we need to find the beginning point of the asymptote? So if you have only one asymptote, then that thing is parallel to the real line itself, so you don't have to find the intersection of single asymptotes, all right? Another question is that, for example, when we have a certain portion of the real axis not included on the root locus, can lines of the root locus go above it? So if you have So the interval which is included in the real axis only bounds that part of the real axis. So it doesn't say anything about what's happening above or below that. So it's only about what is happening on the real axis. Okay. And Hussein asks, do we have only one? Yeah, there's only one asymptote. So and it has the angle pi. So the starting point, there's no starting point for it. So, and remember that the asymptotes are important when s goes to infinity and k goes to infinity. And Bura asks, okay, one of the questions, branch, what is branch? So branch is these trajectories followed by each of these routes. So every trajectory followed by these routes is one branch, okay? So maybe I can go back to our root locus. So this is one branch, and that, what happened here? Somehow, okay, somehow this plot has changed a little bit, so let me try to combine those. Okay, so this is one branch, this is another branch over here. Okay. Anyway, something happened in a way that I didn't want to have. Let me continue with the other questions. So Bura asked, in breakaway points we have double roots, and where are they? So let me try to show them, Bura. Okay. So the repeated poles happen when these two poles move towards each other and meet at the breakaway point here. And again, these poles move towards each other and meet at point -3. For that specific value of k, for example 9, I have two poles located here. I have double roots here. When k is equal to 1, I have two poles over here of the closed transfer function. Okay, so those are the repeated roots. All right. Ege answered Bura's question. Okay, Bura, s is equal to 1. Nerede tekrar ediyor anlayamadım. Okay, Bura, so when k is equal to 1, s is also equal to 1, then you have double roots over here. Okay. And branch chain neden böyle trackers anlatabilir misiniz? So Nurlan, we just said that we cannot, so we said we can specify some details about the root locus, but you cannot plot, say, the exact location of these trajectories every time. In this specific example, these guys are actually following a circle, so that's a perfect circle. But that's a specific case. But usually, when we're plotting the root locus, if we are following some trajectories, we don't know the details of these trajectories. We know, for example, break-in points, we know the intersection with the imaginary axis, we know the beginning and end points, but we don't know what's happening in between these lines. So we just combine them. They're going to be solid lines over there. For this specific example, this is a perfect circle. If you write down the equations for that, you will see that it follows a circle. But in other cases, that in other root locus that we plot in the previous examples, we cannot give the exact trajectory of the root locus. These are approximations. Good. Are there any other questions? Any questions? Oh, Okay, so Burhan asks another thing. So Burhan, maybe you can send me an email and I can answer your question explicitly. Okay. So once you inspect transfer function, what you see is these are the open loop poles. So you cannot say anything about the closed loop poles so far before plotting the root locus. So you put the open loop. So the open loop transfer function only gives you those purple points. It says nothing more than that. Then you continue where these pole locations move by plotting the root locus. And then you see that when these guys are moving together, they meet at a certain point. Maybe that answers your question. All right, so let's continue with the example if I can find the correct layer. So okay, so in our next example we have the following characteristic equation. Sorry about this characteristic. So we have the characteristic equation as s to the power 4 plus 3s cubed plus 3s squared plus s plus k equals 0. And we would like to sketch the root locus as k goes from 0 to infinity. Okay. So how should we approach this problem? So we should first write this thing in the known form, right? I should write this thing as d of s plus k n of s equals 0. So then what is d of s then? So d of s is equal to this guy over here. So it is s to the power 4 plus 3s cubed plus 3s squared plus s. And that is equal to s times s plus 1 cube. How about n of s? So this is k times 1, so n of s is equal to 1. So there are no zeros here, okay? And for example, we can find the number of asymptotes. So let's try to find the number of asymptotes is the absolute value of n minus m, and that is equal to, so this is 4th order, 0th order, so there are 4 asymptotes that we have, okay? And again, number of branches is also 4. Number of branches is also equal to maximum of m and m, that is also equal to 4. So there we'll see 4 poles moving around in our root locus, and the angle of the first asymptote, is equal to pi over n minus m, right? So it is equal to pi over 4, and angle between the asymptotes is equal to 2 pi over 4, so it is equal to pi over 2. So if we make a rough sketch of that, so our first asymptote is going to have a pi over 4 over there, and I will have 4 of them. The angle in between the first one and second one is equal to pi over 2. The angle between second and third one is equal to pi over 2. And the third and last one will be pi over 2. So that will be the picture. But we don't know where this thing gonna happen. We need to find the intersection of the asymptotes, right? So let me do that. So intersection of the asymptotes is equal to summation of poles minus summation of zeros divided by n minus m. So summation of poles is equal to minus 3, right? And summation, since there are no zeros, summation of zeros is equal to 0, and n minus m is equal to 4, so it is equal to minus 3 over 4. So apparently this point is minus 3 over 4. All right, so let's try to sketch the root locus to the right of it over here, if that makes sense. So here is our S-plane. let me place the poles and 0 location. So I will have 1 0 over here, and I will have triple zeros over there. So it is something like this. Point -1. Let me have a look at the questions. Okay, so again, you can think the way you are comfortable with it. It's all fine. Both are fine. So let me continue with plotting the part of the real axis included in the root locus. So if I pick a test point over here, to the right of it there are no poles or zeros, so it's not possible. If I pick a test point over here, to the right of it I have only one pole, which is an odd number. So this part is included in our root locus. Okay. And if you pick any test point over here, you won't see, you will have 4 poles or zeros to the right of it. Therefore, this is not included. This part of the real line is not included in the root locus. We said that the intersection of the asymptotes is at -3/4. So this is -3/4. And at that point, we will have 4 asymptotes with those angles. All right, and then we need to find, for example, how will the poles are going to move. So we know that each of these poles are going to follow the asymptotes. We have 3 poles, and they will all follow the asymptotes. But first they will move on this real line, and then continue further. Okay. So the thing is that they will break away at a certain point over here, and then they will follow the asymptotes. So let's try to find the break in or away points, and then maybe we can continue. All right. So before plotting that with detail, I will find the break in and away points. So break in away points. Okay, we don't have any questions. I checked also that one. So we're going to solve the equation d prime of s n of s minus m prime of s d of s equals 0. So d of s is over here, so d prime of s is equal to 4s cubed plus 9s squared plus 6s plus 1 times n of s is equal to 1, and m prime of s is equal to 0. So minus 0 is equal to 0. Okay. And this is so apparently this is equal to s plus 1 squared times 4s plus 1 equals 0. And we have the roots as s equals -1. Can write it down right here more comfortably. So we have s equals -1, and here we have s is equal to -1/4. And s equals -1, if you check the k value, it will give you k is equal to 0. And the other one, if you check the k value by putting, how do you check the k value? By the way, you check this, right? d of s plus k n of s equals 0. Okay. And then k is equal to 0.1, right? So these are the break-in and away points, and those are all included in our root locus. So apparently these 3 poles break away immediately when k is equal to 0, s is equal to -1. They separate immediately, okay? And if we increase k further, they move towards each other. So let me plot over here. So this pole is going to move here. One of the poles are going to move there. These 2 guys are going to follow these asymptotes directly. Okay. The other one Sometimes like this. Maybe I shouldn't put an arrow there, so I will do just a regular thing that we did here. And this is going to be the other branch of the root locus. They will be symmetric. Okay. And they will follow the asymptotes over here. And these are going to meet at a certain point, which is s is equals to minus 1 over 4. Minus 1 over 4. And then break away later. So then they will break away and follow the asymptotes. Okay. And this guy as well. So that will be the our root locus here. And the last thing that we need to check is the intersection with the j omega axis. And once again, you can do it by applying Rauth-Hurwitz method. Okay, so we write it over here. So let's find the intersection with the j omega axis. So d of s plus square plus s plus k equals 0. To the power 0 is equal to k. Coefficient of s cube is equal to 3. Coefficient of s term is equal to 1. I will compute this guy over here, right? So this is equal to what? 9 minus 1 divided by 3. So I will have 8 over 3 here. 8 over 3. And if you compute this guy, since this is equal to 0, that k is going to come here if you make the computations over here. So this will be k simply. Okay, and let's continue further. Let me try to open up more space here. So this is s to the power 1 term, and this is the s term over here, s to the power 0 term over here. And if you compute this term, let's say this, that is equal to 8 over 3 minus 3k divided by 8 over 3, and that is equal to 1 minus 9 over 8k, right? So this is equal to 1 minus 9 over 8k here, and this is equal to k, so because this will be 0 and k was going to come here directly. Alright, and for stability, as you already know, I need to have all the elements in the first row, so the first column of the Rauth-Hurwitz method to be positive, and I can see system is stable when k is between 0 and 8 over 9, right? So I can write here, so for k values between 0 and 8 over 9, system is stable. And once again, when we have k equals 8 over 9, and k is equal to 8 over 9, we have a 0 row. We have a 0 row. And if you have a 0 row, you can go one step up and construct the auxiliary polynomial here. So p of s is equal to 8 over 3 s squared plus k, which is equal to 8 over 9. It's equal to 0. Okay, and from there you will have the s to be equal to 1 and 2 square root of 3j. Divided by 3. Okay, so if we go to our root locus, so we can write down these points as j, and this is minus j square root of 3 over 3. Eren dediğiniz doğru. Hani so Eren asked that, so where are the poles that are coming from? So we have 3 poles here, so I plot on top of that. So remember that we have s plus 1 cube, so I have 3 poles over here. So one of the poles break away and follow this asymptote. The other pole breaks away and follow this asymptote. The remaining pole starts to move towards the other pole on the real line, and they meet at the point minus 1 over 4. That's how that's we computed from this equation and check the k value. So when k is equal to 0.1, if I can write that thing down. So here is k is approximately 0.1. Okay. These two poles meet here, we have double roots here, and they break away, and they start following the asymptote. We don't know the exact trajectory over here, but we know where it intersects the imaginary axis, and we found the intersection with the imaginary axis by Rother's method, and apparently it is square root of 1 over 3, and that happens when k is equal to 8 over 9, so right here. So here k is equal to 8 over 9. And when k is beyond 8 over 9, so if I pick k values greater than 8 over 9, then on the Roth-Hurwitz first column, on the first column of the Roth array, I will have, this is a negative number, so 2 sign chains. So this is plus, 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 negative, plus, so I will have 2 sign chains, which means that 2 poles will have positive real parts. And I see those poles are these guys over here. So for k greater than 8 over 9, those 2 poles are moving to the right half plane and making the system unstable.